Actually, most of you missed many points. Yeah. So let me explain the details. All right. First question, number 21. Suppose that a select star statement returns a SQL table with 4 columns. How many different projections can we get from this table with at least 2 of the columns? Here, the main question is in that order, the definition of projections. Most of you give me the answer without considering the order factor. Now, let me explain. Yeah. All right. Yeah, because most of you give me a number using the combinatorial number, choose 4, 3 from 4, that kind of thing. 4 choose 3, yeah, 4 choose 3, like that. Remember, if you recall the meaning of the combinatorial number, here, for example, because many of you write things like this, combinatorial number, right? Choose 3 from 4. This expression without considering the order, right? Yeah, because in this way, the order is not important. C1, C2, C3, that's the same thing as C2, C3, C1, right? When you use this combinatorial expression. But think about in our projection, the definition, the order matters. The order is important. Okay, yeah. All right, so here, because we have 4 columns, and we need to choose the projection with at least 2 of the columns. Okay, yeah. So let's see 3 cases. The first one, the projection with 2 components. Yeah. The second case, the projection with 3 components. Right? Yeah. And the third one, the projection with 4 components. Okay, yeah, here. All right. Then, when we count the numbers for each case, we do not use the combinatorial numbers. We use the product rule in counting, product rule, yeah, because 2 components projection, the first one, there are 4 choices. The second one, 3 choices. 4 times 3 equals 12. Here, we treat different order as different projection. Now, C1, C2, in this case, C1, C2 is different from C2, C1. Yeah. Similarly, case number 2, 4 component, 4 cases for first component, second component, 3 cases, 3, and the third one, 2. So that's 24. And the last one, 4 factorial, also 24. Okay, yeah. So the total, 12 plus 24 plus 24 equals 60. Yeah. But when you do not consider the order, that number is much smaller. Yeah. So that's most of you did in that way, projection. Order is important. Yeah. All right. Yeah. Okay. Yeah. Next question. Yeah. Next question. Oh, yeah. All right. Which of the following the SQL day values is valid? Yeah. Some students didn't notice the valid dates on the calendar. Not many, yeah, one or two students, yeah, two or three, probably two or three students pick those dates that do not exist on the calendar. For example, this one, right? Because year 2014, it's not a leap year, right? Yeah, because 2014, it is not a multiple of 4, not multiple of 4. So it's not a leap year. If it is not a leap year, then in February, there is no 29th day. So it's not valid. Another question, yeah, another student also picked D. Look at June. We never have 31st in June, right? Yeah, only 30 days in June, but one student picked the option. Yeah. All right, so A is correct. B, we know it's not a SQL format, right? Yeah. B, it's not a SQL. Oh, Krishna Reddy is here. Yeah. All right. Okay, yeah. Yeah, so that's this one. Yeah, not that hard, but most of you got this one correctly. Only 2 or 3 missed this question. The next one, yeah, the answer is true. Yeah, but so many students, I estimate about 1/3 of you pick the false because you are used to the 2-value logic. Here in SQL, we use 3-value logic. Yeah, that's the only thing. So not a false means you have true and unknown. But for unknown, we do not select it, right? We only select when our Boolean expression takes true value. Yeah. So there is still a chance that this tuple is not selected. Yeah, because still a chance tuple not selected, it's unknown. Okay, so it is true. Yeah, but for those who select the false, I'll give partial credit. 2 points. No, 2 point partial credit. Okay. All right. Yeah, because this fact is important. Remember, so the last time we have a question, select count function. Remember, count function, the column number X. Yeah. When we do this one, yeah, if this column value has the null value, sorry, yeah, null value, null value, then it is not selected. Okay. And we know null value directly connect to an unknown case, right? Directly connect to unknown case. Yeah. Because null value calls unknown Boolean value. When you have an unknown Boolean value, you do not select it. Okay. Yeah. Yeah. All right. Yeah. This one, composite secondary, yeah, also a large number. Most of you missed this question. Yeah. Assume that a SQL table with 5 columns, the first column is the primary key, and the remaining 4 columns are non-key fields. So itself, the single column itself is not a key. Yeah. So non-key fields. Yeah. If we want to construct a composite secondary key, that means we need to use at least 2 columns from the 4 non-key fields. Yeah. Yeah. How many different possible secondary keys with at the most 3 columns can we have? 3. So we do not consider the 4 column cases. Yeah. 2 column cases and 3 column cases. Yeah. So only 2 cases. The first one, 2 column cases composite key. And the second one, 3 column composite key. Yeah. The same as that question number 21, we need to consider the orders when we define composite key. So here, order also important. If you switch the order, we treat as 2 different composite keys. Okay, yeah, yeah, because that's the definition for that tuples. The component orders are important. Okay, yeah. So if you change the order, we treat as different tuple values. Yeah. Yeah. So similar to our question number 21. Yeah. So if you know tuple, inside tuple, here I'm talking about inside tuple. Not a list of tuples. So not, because in the table, we consider a list of tuples. That's different. Here, inside tuples, the order of components is important. Yeah. So based on that understanding, then you should not use combinatorial numbers. All right, yeah. So you should still use our product rule in our counting. The first component, 4 cases. Yeah. Second, 3. 12. 4, 3, 2, 24. Yeah. So the total, 12 plus 36. 48. Sorry, not the, yeah, I mean, I already had it up. Yeah, yeah, I feel strange. Yeah, yeah, because it's a contradiction with our question number 21. Yeah, 36. Otherwise, yeah. All right, yeah, order, yeah. So here you can see the main point, yeah, in your understanding, which place we should consider the order factor, and what situation we do not consider order factor. A list of tuples in a table, in that situation, we do not consider the order. Yeah, and this concept, I remember I gave you similar question in a quiz question, but I just ask you, give you two cases. List of attributes. Second option, a list of tuples. For which one the order is important? We have that question in a quiz. Yeah. That one, a list of attributes, the order is important. That's the answer. Yeah. But here in these two questions, so we use that piece of knowledge. Yeah. That question, I just ask you in an abstract way, but here, these two questions, we need to use that concept. All right, yeah. Okay. Last question. Last question, actually the answer is 4, but many students give me 5. The reason is not considering this auto increment case. I put in a parenthesis. So first, I like to explain that auto increment, this concept. Auto increment, primary key. For MySQL. For other DBMSs, it may not be available. Yeah, it may not be available. Yeah. All right. Yeah. So here, actually, this concept is very useful. Yeah. The reason because you do not have the experience in the real world applications. Yeah. Here, you study this topic in this class. You do not have the hands-on experience. So for that reason, you do not have big impression on this concept. Yeah. For myself, because I developed some real-world projects. So I try different things, but I noticed sometimes when we design tables, if we use auto increment primary key, it's very convenient. First, the auto increment primary key, based on the name, the DBMS generate the primary keys automatically. First, DBMS generates the auto increment primary key in this 1, 2, 3, automatically. So that's the first thing. After that, think about the good thing is there you have the primary keys, right? This table, you have the primary keys, very convenient to manipulate the data in this table. Because if you do not use this one, think about your table may not have the primary keys. Your table may not have the primary key, okay? Because your table may have the duplicate rows. So in this way, the duplicate rows are avoided. So that's the first benefit. Okay. Then editing, updating, deletion, all pretty straightforward. Okay. So if you can get this auto increment primary keys, very easy, very convenient. That's the first thing. The benefit. the second benefit, yeah. So this is an internal primary key without business meaning. Because it's the generated, it's not original data, right? Yeah. So it's the generated data. It does not have the specific business meaning. Okay, yeah. Yeah, because the main purpose using this kind of primary keys just for data manipulation, for the ease of data manipulation. That's the main reason we use that. Yeah. So then, there is no reason to change its value, right? No reason to change its values, because its values main purpose used to identify different roles. The value numbers, larger, smaller, not that important. Yeah. So usually we do not need to change those kind of primary key values. Yeah. Okay. Yeah. 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 So it's another good property, because when you change primary key values, a lot of things you need to consider, some complexity. For example, foreign keys, right? You know, a lot of things you need to worry when you change the primary keys. You need to worry about foreign keys. Okay. Yeah. But here because we do not need to change the primary keys. So that's another good property for this kind of auto increment primary keys. Or then we don't need to provide its value. And here, because among those 15 rows, 7 of them, we need to provide values explicitly. 8, then the remaining 8 columns, the values are provided implicitly. Okay? Implicitly. So let's look at the cases implicitly. Yeah. The first one, auto increment. That's the implicit way, right? Yeah. Auto increment. Yeah. Primary key. Second, default. With default. Right. With default values. Then we do not need to provide the values for these columns explicitly because they have default values. Okay. The third case, without not null constraints. constraints. Okay, yeah, all right. These three cases adding together should be equal to 8. Yeah, but there is a possibility, you know, these two cases, there's possible some overlap, right? Yeah, yeah. But here we consider the minimum value for K. Yeah, okay, yeah. So auto increment, we know number is 1. Yeah. 3 columns with default value and the K columns with null constraints. Yeah. And there is a possible overlap, possible. Okay, possible overlap. That means 1 plus 3 plus K. If we consider the possible overlap, it should be greater or equal to 8. Yeah. Then K is greater or equal to 4. If there is any overlap, then the K number is greater than 4. But here, if we just look at the minimum value for K, that's just 4. Okay. So that is the way we answer this question. Yeah. Yeah. So for those who give me number 5, yeah, those students, they didn't consider that auto increment. The reason, yeah, because you do not have a lot of experience related to that auto increment primary key. Yeah. That's a good feature, convenient, useful feature. Okay, yeah. All right, yeah. So this is the homework number. Yeah. Then after that, I like to give you some more concept questions. Yeah. 8 more concept questions. Try to show you some other question types. Yeah. Okay. Yeah. All right. Part 2, more concept examples. The first one, when we define a table for any attribute that does not allow the null value, we have to specify the null constraint explicitly. It's false. Here, I hope you know it. Yeah. It's false. The reason is that there is exception for this statement. There is exception, primary key. Okay. The primary key is the exception because for primary key, it is required the primary key cannot be null and you do not need to specify it. Yep. That is in the rule. Yeah. That's the exception for the statement. Yeah. False. Yeah. Number 2. All right. Given a table, even if you cannot find a single attribute primary key, you can always find a composite primary key. False. Yeah. Why? Think about duplicate rows. Duplicate, nobody you can find. There is no key in the table with duplicate rows. Yeah. Yeah. Consider this case. Okay. Yeah. Duplicate rows. Number 3, union OR. When we apply the union OR operator on any 2 union compatible tables with n rows and m rows, respectively, we always get a table with n plus m rows. True. It's true. Here, the main concept here is we use the union all, and this operator treats the duplicate rows as different copies. Because when we use the union all, some of the rows could be duplicate, could have the same tuple values. Although they have the same tuple values, but it is treated as copy 1, copy 2, copy 3, and so on. Because we treat those tables as multisets. Not sets, multisets. In the multisets, the elements with duplicate values are treated as different copies. So for that reason, the total number n plus n, the sum of the total number of rows in these two tables, because duplicates are not eliminated for the multisets. Okay, all right. Number 4, it is possible for a multiset table with duplicate rows to have a primary key if we consider the composite type primary keys with duplicate rows. Yeah, here. If you know there are duplicate rows, then there is no way you can find composite primary key. Because if you can find a duplicate, if you can find a composite primary key, that means all the tuple values must be unique. No duplicate rows. That's a contradiction. Contradiction with the duplicate rows. No. With a primary key, you can identify different rows. That means the tuple values are different. But you know there are duplicate rows. Yeah. Here, yeah, I hope in this question you do not confuse with the previous one. That is, the duplicate rows are treated as different copies. Do not confuse with that. That rule is used when the multiset elements are processed, but those duplicate rows, they have the same values. Same values, that means you cannot separate those rows by their values. If you look at the values, you cannot separate those rows. For that reason, that means there is no primary key. Yeah, because if you have primary key, you can separate those rows by looking at the primary keys, right? Yeah. So do not get confused with question number 3, different copies. Those copies are, they have the same tuple values. All right, yeah. Okay, yeah. Next question. Yeah, here, We want to understand the partition concept. So this question, we need to really calculate carefully. All right. Given a set with 3 elements, we consider the type of partitions of it. First, we need to be familiar with the properties of partition concept. With a partition of a set, what properties should we have for a partition? We need to review that, which can be written as S equals A union B. A union B. All right? With cardinality of A. The number of elements in A, we use that. Vertical by absolute value representation, we call it cardinality. The cardinality of A equals the cardinality of B equals 3. How many such partitions can you find? So it's a counting question. Counting question. All right, partition. All right, so here to calculate that, then order here, the order factor another time. Remember, at the beginning, we talk about the order, but here, because for the partition, when we consider partition of a set, okay, so here, order of elements. Is not important. Here, because in a set, so A1, A2, A3, if we change the order, A3, A2, A1, the same set. Okay, we treat as the same subset. If we change the order, so that's the concept for a set. Okay, all right, and here, based on that, we can use the combinatorial number, right? Combinatorial number. Choose 6, choose 3. So look at that. We need to choose 3 elements from S to make subset A first. Then the remaining 3 elements, we put it in B. Okay, so that means 6 choose 3. This number of cases for set A, and then after that, after we take 3 elements away, we have 3 elements left. So for B, we just select 3 from 3. That's for B, right? But be careful. There is, so, be careful here. Why? Because the cardinality of A and B, they are the same. They are the same, So look at this example. So if we have A equals A1, A2, A3, then automatically B have A4, A5, A6, right? So that's the first case. Look at the second case. If A has A4, A5, A6, then B automatically has the A1, A2, A3, right? Yeah, look at these two cases. Do we treat these two cases as two different partitions or not? Think about that. Two different partitions or not? Okay, yeah. We split the original set in these two subsets. And one is called A, another is called B, but they are essentially the same, right? The split is the same. One subset has A1, A2, A3, another one has A4, A5, A6. Why we treat them as two different partitions? Okay, so these two, they correspond to the same partition. Partition, okay, yeah. Partition. If they correspond to the same partition, but in this expression, we count them twice, right? That means we need to do division by 2. Yeah. Because each partition, you count it twice. You need to remove 1/2. Okay, yeah. So the answer 1/2 times 6 times 5 times 4, 3 times 2 times 1, cancellation, 20, 10. 10 different partitions. Yeah. So be careful. So when you do the counting, right, in this like this, yeah, remove the duplicate partitions. Here we need to remove the duplicate partitions, right? Yeah. Think about that. Yeah. All right. Yeah. And here, if I modify a little bit, then you do not need to do that. Worry about it. Yeah. Here, if I tell you the cardinality of A equals 4 and the cardinality of B equals 2, yeah, because these two subsets, they do not have the same number of elements, then you won't have the situation, the 3-3 case. Yeah, because you cannot switch, right? A, B, just based on the number of elements, you cannot just switch the, those two, the contents of those two subsets to get the same partition. That situation does not exist. So in this one, so you choose 6 choose 4, 2 choose 2. You don't need to multiply by 1/2, all right? Yeah, because no duplicate. In your counting, there is no duplicate partitions. Right? Yeah. Yeah. Okay. Yeah. Question number 6. Yeah, let me give you another version of the question. Yeah. So this version, yeah. I do not erase. I hope you can see it. Yeah. But this time, how many? 10 elements. Yeah, there are 10 elements. S. We have A, B, C, D, 4 subsets in the partition. But A and B, they have the same cardinality, and C and D have the same cardinality. Okay, yeah, all right. How many such partitions can you find? Yeah, so let's use our question number 5. Yeah, so let us use that thinking to answer this question. Yeah, all right. 10 questions. When we choose the number of elements for subset A, 10 choose 3. All right, yeah. Then when we choose elements for B, the remaining 7 elements, we choose 3, for B. Yeah. But remember, we can switch A and B. For the duplicate cases, we need to do division by 2, right? Yeah. Remove the duplicate cases, okay? Yeah. Similarly, for C and D, the remaining 4, choose 4 from 2, and for C and 2, choose 2, you can switch, right? Yeah, you need to remove the duplicate cases, another division by 2 for between C and D, for C and D, okay? Yeah. Yeah. So you calculate in this way. Carefully remove the duplicate counting. Yeah. All right. Yeah. Another case. Yeah. Just special example. Still 4 elements. Okay. S equals A1, A2, A3, A4, A5, A6. All right. But this time, as our partition is like this, A union B union C, okay, yeah, C with the cardinality A equals B equals, yeah, so slow, yeah, C, okay, yeah, equals 2. Oh, yeah. Yeah. Equals 2. Yeah. Yeah. So bad. C. Oh, horrible. Two. Okay. In this case, how to calculate the number of partitions, different partitions. Okay. Yeah. Here, yeah. 6 for A, 6, choose 2. Yeah. Too slow. Yeah. Wow. I don't know if the Zoom problem or my computer problem. Okay. Yeah. 6, choose 2. For B, 4, choose 2. All right. C, 2, choose 2. All right. But duplicates, think about, because they have the same number cardinalities. When you do any permutation, you get the same partition, right? Any permutation in A, B, C, you get the same partition. So you need to remove the duplicate counting by each partition. Actually, you count 3 factorial times because of the permutation of 3 subsets. That's 3 factorial. So you need to do division 3 factorial. Okay. Yeah. So before, when we do that 1/2, actually that's 2 factorial. All right. 2 factorial. 2 factorial. Okay. Yeah. But here, because we have 3 subsets with the same cardinality, so 3 factorial. All right. Yeah. Okay. Yeah. All right. Then next question. Yeah. Yeah. But this question, yeah, I like to, yeah, actually this question and the next question, same. Oh, yeah, different. Yeah, 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 yeah. Let me, yeah, because the time I have, yeah, yeah, I need to go a little faster. These are last two questions. Yeah. First, still partition concept. Yeah, but the condition we know we have this equality condition. Now the question, we want to see if this ABC form a partition or not. Okay, yeah. For the partition, yeah, let me review what conditions it should satisfy for a partition. First, whole set coverage. Yeah, we have it covering the whole set. Yeah. The union of the subsets covers the whole set S. So the first condition is satisfied. Whole set coverage, that condition is satisfied. Okay, all right. Second condition, each subset must be non-empty. Each subset cannot be empty. Non-empty condition, given non-empty subsets. So our second condition also there. The third condition, no overlapping, no overlap. That means the intersection of every two sets should be empty set. Empty, and A intersect B should be empty, empty, okay? And a B intersection with C also should be empty. Okay. And the third condition, we don't know. In this question, we don't know. If we can answer the third condition, if we can figure out the third condition, then we can make the answer. Okay, all right. But with the given equality, can we see that? Here, I like to give you one formula. Yeah, all right. A union B cardinality equals the cardinality of A plus the cardinality of B minus cardinality of A intersect with B. Yeah. This formula, okay? We have this formula, okay? Yeah, all right. It means because the cardinality of this A intersection with B, it's greater or equal to 0, right? Yeah. Because we know cardinality of any set should be greater or equal to 0. So this one should be greater or equal to A cardinality plus B cardinality, right? Okay, yeah. Similarly, union with C, A union with C should be less than or equal to cardinality of A plus cardinality of C. All right, and the B union C cardinality less than or equal to B cardinality plus C cardinality. All right, yeah. Let's add up these three inequalities. So we have the left-hand side. So here I do not copy, okay? Left-hand side less than or equal to the right-hand side. How about that? But it's inequality. But what we are given is the equality. That means each inequality should be equality, right? Each inequality before should be equality. That means the cardinality of, here. That means cardinality of A intersection with B should be 0. Because it's an equality, right? Similarly here, A intersection with C, intersection with C, should be 0. And B intersection with C should be 0, right? 0 means empty, right? These three intersection subsets should be empty. That means the third condition is satisfied. All three intersections should be empty. That means it's a partition. Three conditions are satisfied. Think about that. I do not talk about the next question. So this is our last question. All right. The next question, let's forget about it. Even the bad thing is, my handwriting too slow. Probably related. One thing is this Zoom. Zoom recording use a lot of memory, the first thing. Second, the memory of my laptop, relatively small, 4 gigabytes. That's relatively slow. So that causes the slow writing problem. Otherwise, if my memory is larger, the Zoom use too much memory recording. All right, so let's stop right here.